Alright, the third and last problem of this type. This is another z-test. This is another case where we're doing a hypothesis test on the mean and we, for some reason, know the sigma of the original population. So let's just shoot right through this. Let's just read it, write it down. A manufacturing process produces ball bearings with diameters that have a normal distribution with known standard deviation of 0.04 centimeters. Ball bearings with diameters that are too small or too large are undesirable. In order to test the claim that that mean ball bearing diameter is 0.5 centimeters, we're going to perform a two-tailed hypothesis test at the 5% level of significance and assume that a random sample of 25 gave a mean diameter of 0.51 centimeters. So let's write down, let's go A, write down the null and alternative hypothesis. The null, always equal to 0, is always equal. And in this case, it's the status quo. Mu is equal to ½ centimeter. And the claim is from this sample that, and the claim in what we're interested in knowing is if it is 0.5 centimeters or not. So H1 is not. Again, H1 can never have a equal sign in it, and it doesn't has a not equal sign. This is a two-tailed test. Yeah, and because of that, when we find the critical values, the lines in the sand, we're going to split that 0.05 significance into two parts, 0.025 and 0.025 on the left and on the right. We'll use inverse norm, 0.02501, and get what by now should become pretty familiar to you, plus or minus 1.96. Now all that's left is to calculate the test statistic based on that sampling at 0.51 centimeters. So the test statistic is the z-score, x bar minus mu 0 all over the standard deviation or the standard error of the sampling distribution, which is sigma over square root of n. X bar is 0.51, mu 0 is 0.5, sigma is 0.04, and n sample size is 25. Let's plug all those numbers into z-test. We find that z-test is 1.25. If we just look at the schematic, z-test falls in the non-critical region between the two lines in the sand, right? Not in the two tail critical regions. It's in the non-critical region, and what that means is you fail to reject the null. You hold on to the null. This sample of 0.51 is fairly close, or close enough based on our definition of closeness, to be essentially indistinguishable from the null 0.50. The difference between 0.50 and 0.51 is just sampling error. That's it. Let's move on to some slightly different types of problems.